limits at infinity and horizontal asymptotes. With the last lesson looking at limits, infinite limits, where an answer was infinity or negative infinity, this lesson goes over what happens when x approaches negative infinity or positive infinity, which lends us to the other asymptotes that you all know and love, the horizontal asymptotes. So let's take a look at what these limits look like. So a very quick example, the limit as x approaches infinity of 1 over x is 0. And you can see that over here, this black arrow going right. The further and further this graph goes to the right, the closer and closer this graph gets to 0. The y values will approach 0. And with this other example, the limit as x approaches negative infinity of 1 over x is also 0. So as the function travels further and further left, the y values will get closer and closer to the x-axis, which means the y values are approaching 0. And a very quick note on this slide, you notice that in the previous slide, if you try to directly substitute the infinity in for x, you'll end up with a number over a positive infinity or a number over a negative infinity. If this happens, then the limit is 0. And this is summed up in the theorem here. The limit as x approaches infinity of 1 over x to the n power equals 0 for any positive n value. And the same thing is true if you approach negative infinity. On to some examples. Examples for finding limits at infinity. So all three of these examples will use the same idea. In order to find a limit at infinity, you will need to divide the numerator and denominator by the biggest power of x in the denominator. In the first example here, the limit as x approaches infinity of this fraction, if you look at the denominator only, the highest power of x is x squared, x to the second power. So you can rewrite the limit like this. And as you can see, the only difference between this fraction and this fraction is that both the numerator and denominator were divided by x squared. Now you can separate this entire numerator now, this fraction in the numerator, into 1, 2, 3 different terms, each having a denominator of x squared. And in the fraction in the denominator, you can divide this into 1, 2 different terms, because there's only one term in the denominator of each fraction. And that's going to be a very important idea, being able to split up a fraction into multiple fractions using one term. So that new limit will look something like this. So the fraction in the numerator was separated out to 3 terms. The fraction in the denominator was separated out into 2 terms. Now you should simplify each singular fraction individually to get a limit that looks like this. And here you can see that each individual fraction was simplified. And on the previous slide, there was a theorem that stated if you have a number over x as x goes to infinity, this entire fraction goes to 0. So all of these fractions go to 0 as x goes to infinity, which leaves us with the limit equaling 2 over 1, which is just Now in the next example, I will not be taking as many steps to get to the answer, but the similar process is done. So we will take the numerator and denominator and divide by the highest power of x in the denominator, which is x cubed. So that fraction looks something like this. If you divide x squared by x cubed, you get 1 over x. If you divide negative 3x by x cubed, you get negative 3 over x squared. And if you divide negative 5 by x cubed, you get negative 5 over x cubed. And you can use the same rationale for the denominator. So now, any term that's left over with an x in the denominator, as long as x is going to either positive or negative infinity, turns into a 0. So this fraction goes to 0, this fraction goes to 0, this fraction goes to 0, this fraction goes to 0. And that's a lot of zeros being added and subtracted in the numerator over 1 minus 0 in the denominator gives you a 0 over 1, which is 0. And in the last example, you'll notice that the highest power of x in the denominator is x squared. So when you divide the top and the bottom by x squared, you'll get a limit that looks something like this. And you'll see once again that any term that's left over with an x in the denominator, these three terms right here, will go to 0. So that goes to 0, that goes to 0, that one goes to 0. So we're left with a limit as x approaches negative infinity of x over negative 1. Well, if you substitute this negative infinity in for x, you'll get a negative infinity over negative 1. And a negative divided by a negative is positive. Infinity divided by 1 is still infinity. So the final answer will be infinity for this example. One thing you may remember from a previous math course is how to find a horizontal asymptote for a rational function. So what I'm about to say only works if you have a rational function. Again, a polynomial divided by another polynomial, like here, here, and here. You know the rule that if the degree in the numerator is equal to the degree in the denominator, then the ratio of the leading coefficients will be the horizontal asymptote. In this case, the degrees are equal in the numerator and denominator. The leading coefficient in the numerator is 2. The leading coefficient in the denominator is 1. 2 over 1 is 2. And you can use those similar rules that you've heard from the previous math course, like when the degree in the denominator is bigger than the degree in the numerator, then the horizontal asymptote is at y equals 0. And when the degree in the numerator is bigger than the degree in the denominator, then there is no horizontal asymptote, thus resulting in infinity for our limit here in the last example. In these two examples, you may notice that they look extremely similar. The difference is, in the first example, we're taking a limit as x approaches positive infinity, and in the second example, we're taking a limit as x approaches negative infinity. Now, we will use the same technique that we used in the previous three examples of dividing by the highest power of x in the denominator. But we need to do it a little bit differently than we did before. You'll notice that in each of these examples, there's a square root in the numerator, with an x squared inside, and the denominator is just linear. So inside of the square root, there's an x squared. And if you know one thing for sure, it's that the square root of x squared is the same thing as x. Except it's almost true that square root of x squared is the same thing as x. Mathematically, the square root of x squared is equal to the absolute value of x. And the absolute value of x is defined in a piecewise manner as x if x is bigger than or equal to 0, and negative x if x is less than 0. So we will have to keep this fact in mind when we are going through and dividing what's this piece up here. So in the numerator, we will write something that looks like this. The limit as x approaches infinity of x squared plus 4, the square root of all that. On the numerator, we will divide everything by the square root of x squared. And in the denominator, we will end up dividing x minus 3 by the absolute value of x. Now, before we can go any further and start combining and dividing things out like we did in the previous examples, we need to figure out which x are we going to use. Are we going to use the positive x, or are we going to use the negative x in place of this absolute value of x? To figure that out, you need to look no further than where the limit is going, where x is going. X is approaching positive infinity. So since x is approaching a positive infinity, that means the x's are going to be bigger than 0. That means we will be using x when we divide through a limit that looks like this. Anytime you divide a square root by a square root, you can combine these square roots into one square root. So I've done that, and I've also already broken the fraction that would have been inside the square root into two separate fractions. And in the denominator, we already said that since this is going to positive infinity, that means we will use a positive x to divide over here. So the absolute value of x becomes positive x, and this fraction already got split into its two separate terms. So now, all we need to do is simplify the fraction to look something like this. And we can still send this fraction to 0 and this fraction to 0, leaving you with a square root of 1 over 1, which is 1. So as the graph goes out far right as x approaches infinity, the y values are approaching 1. I'm going to give you a few seconds to pause the video so you can try this example here. This example is done very similarly to this example up here. Keep in mind that the square root of x squared is equal to the absolute value of x, and that you'll have to choose one or the other of these, either positive x or negative x, based on what the sign of infinity is. Go ahead and give this one a shot. All right. To start this example, you should divide the top and bottom by the same thing. It's going to look a little different, but we will divide the top and bottom like we did up here in this first example. It'll look something like this. And since this time the x is approaching negative infinity, the absolute value of x will turn into a negative x. As x is less than 0, we will use the opposite of the x. The next limit looks something like this. And if the fractions are simplified, oops, I forgot the negatives. If the fractions are now simplified, then the new limit will look something like this. And we can still send these limits or these terms to 0, and you end up with a square root of 1 over negative 1, which is negative 1. So as the function goes further and further and further right, the y values approach 1. As the function goes further and further and further left, the y values approach negative 1, which means this function has two horizontal asymptotes. In the previous two examples, you saw that the absolute value of x squared, the square root of x squared equals the absolute value of x, and that gave us a piecewise function for the absolute value x and negative x if x was bigger than or equal to 0 and x was less than 0. And these helped out figuring out which one you should use, and we use the top one if x goes to infinity and the bottom one if x goes to negative infinity. Well, this square root of x squared equals absolute value of x is not the only version that you can see. You can see something like this, where you have the square root of x to the fourth equals the absolute value of x squared. But if you look at the absolute value of x squared, it just equals x squared all the time, because the quadratic function is already non-negative. And by that, the y values are all either above or touching the x-axis. And that's it. These are the only two scenarios you will run into in Calc 1, but the pattern will continue. And if you're interested about that, then you can email me for more information. On this slide, you can see that there are 3 examples here. I am going to give you a few seconds to pause the video so you can try these for yourself to see how well you are progressing through the material. Once I stop speaking, you will have about 5 seconds to pause the video, and I will work these exercises on the other side. In the first example, you can see that there is a polynomial over a polynomial, making this rational. And you can find the limit at infinity here by dividing the top and bottom by the highest power of x in the denominator. That being said, the new limit will look something like this. So here's what it looks like when you divide the top and bottom by x, and then you can break that one fraction up into three different fractions in the numerator because we started out with three different terms. And in the denominator, you can break that fraction up into two fractions because the denominator started with two terms. The next step would be to simplify each of these little fractions, if you can, to get a limit that looks like this. So here are all of these simplified fractions, and this limit is x goes to infinity. So from the previous lessons, you know that this goes to 0, this goes to 0, and that leaves you with an x squared negative x squared plus 6 all divided by negative 1. So again, we've got this situation where we have two terms in the numerator and one term in the denominator. So we can split this up into two different fractions and divide the negative x squared by negative 1 to get a positive x squared, and divide this 6 by negative 1 to get a negative 6, for a limit that looks something like this. We have the limit as x approaches infinity of x squared minus 6. And these are all negative infinities, I just realized. There we go, as x approaches negative infinity of this new polynomial. Now, when you substitute negative infinity in for x, this is going to look something like negative infinity squared minus 6. And this is a good way to think about where the limit is headed. So when you substitute negative infinity in for x here, negative infinity squared becomes a positive infinity minus 6. If you subtract 6 from infinity, guess what? You're still going to be at infinity. So the end answer here for the first example is the limit approaches infinity. You can do the second example on this page in the same way. I will slowly reveal some steps for you. The answer for this second example is negative 17 over 3. For the last example, I will also slowly reveal some steps. The final answer here is negative 1 over square root of 2. That is because from the very beginning, when you divide the inside of the radical by x squared, the square root of x squared, it's actually the same thing as the absolute value of x. So we divide the inside by x squared and the top terms by absolute value of x. And the absolute value of x equals negative x because x is approaching negative infinity. That being the case, we divide the top by negative x, and then a number over x to some positive power will go to 0, so these terms disappear. And this term simplifies x over negative x to negative 1. So we're left with a negative 1 over the square root of 2. So the final answer here, negative 1 over the square root of 2. I would urge you to try this last example again as x goes to positive infinity, just to see what the answer will be. Horizontal asymptotes. The definition in calculus of a horizontal asymptote is the line y equals L is a horizontal asymptote of a function f if either the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. And this definition resembles pretty well what horizontal asymptotes would be if you go back to the last lesson. It is very similar to the definition for vertical asymptotes. So you might be wondering, how do you find horizontal asymptotes of functions using calculus? All of those examples that you've done on the previous slides, that is what you have to do to find horizontal asymptotes. The only hitch is that you need to find the limit as x approaches positive infinity of f of x and the limit as x approaches negative infinity of f of x. So you must find both. And this is because of the last few examples that you've seen that have a square root in the numerator or denominator, there's a chance that there could be more than one horizontal asymptote. So you will have to go through and find the limit as x goes to positive infinity and the limit as x approaches negative infinity of f of x. You've done enough practice on this already. You will have some more practice in a little bit. So you will not be asked to find any horizontal asymptotes. You just have to make sure that when you give an answer, it is the full-on equation, y equals some number.